Hi, welcome to an online webinar on the fraud detection with graph neural network solution. My name is Soji Adeshina, and I am a machine learning developer at AWS ML. In this video, we will explore how to solve fraud detection using graph neural networks on Amazon SageMaker and Deep Graph Library. Let's start with a bit of background on fraud detection. Fraud detection is a problem that affects many online businesses and costs them billions annually. Some examples of fraud and malicious behavior online include financial fraud, which is when fraudulent users make fraudulent financial transactions using stolen credit cards and so on. We also have fake reviews, when malicious users intentionally provide reviews to fraudulently elevate or sabotage a product or service online. We had bot attacks, when hackers or fraudulent users create a collection of automated services or internet-connected devices to get unauthorized access to products and services. Then there is account takeovers, when malicious users gain illicit access into a legitimate user's account in order to take advantage of the legitimate user's resources. Spam attacks are also another form of fraud and abuse online, where malicious users can send massive amounts of unsolicited requests to legitimate customers, and so on. This fraud detection solution is designed to be able to tackle all these various kinds of fraud and abuse in an online system. Many businesses take a rules-based approach to combating fraud online, but many of these existing approaches can have some severe limitations. First, many existing methods are not always sophisticated or flexible enough to detect the range of fraudulent or suspicious behavior online. Second, many fraudsters can evolve or adapt to simple, rules-based or features-based methods. For example, fraudsters can create multiple coordinated accounts in order to circumvent limits that are placed on individual accounts. However, fraudsters are not able to hide their behavior with respect to the full interaction graph. For example, fraudulent accounts that are often connected to other objects in the interaction graph can indicate guilt by association. We can also combine weak signals from individual nodes in a connected component to derive stronger signals about those nodes. Fraud detection with graphs is effective because we can detect patterns like node aggregation, which is when a particular user starts to connect with many other users or entities in the interaction graph, and activity aggregation, which is when a bunch of suspicious users or accounts begin to act in tandem. Before we delve deeper into fraud detection with graphs, let's go over some basic definitions of what graphs are and why they are useful. So a graph is an abstract data structure that can be used to represent a set of entities and relations between those entities. For example, the image on the left represents a set of individual entities that have some link or relation between them. And for the image on the right, we have a network of different kinds of entities. We have individuals, as well as devices and financial institutions. Because graphs abstract away the details and focus on the relations or link between entities, they are a convenient and flexible way of encoding information. The entities represented in the graph are referred to as the nodes of the graph, while the link between the nodes are referred to as the edges. A graph that has a single type of node or edge is called a homogeneous graph, while one with more than one node type or edge type is called a heterogeneous graph, like the one on the right. With heterogeneous graphs, we can easily model real-world processes or interactions. In fact, lots of data already exist as graphs or networks, and this can be harnessed to uncover new information and solve problems. Graph learning or learning on graphs is the process of inferring new properties of graph components using the information that's contained in the graph itself. One important class of graph learning problems is node classification. Node classification can be described as the process of assigning or predicting node labels to all nodes in a graph where we have a given subset of labeled nodes. This is very similar to other classification tasks in machine learning, except that in this case, the objects that we're classifying are the nodes of a graph. And this formulation works very well for our fraud detection use case, because we can frame the fraud detection on graphs problem as a problem of predicting the labels, for example, fraud or non-fraud, for the nodes in the graph, using a subset of the nodes that already have labels as the training data. Formulating the problem this way makes it into a semi-supervised learning problem in machine learning. And in order to use machine learning models or algorithms on the graph nodes, we need a numerical representation for the nodes. Now let's dive into how these numerical representations are derived. Now, we know that attempting to solve node classification using machine learning requires representing the nodes numerically in a way that's useful to the downstream machine learning model. This numerical representation for the node is also called a node embedding. Usually, a node embedding is a dense numerical representation in a continuous vector space with a much smaller dimension than the cardinality of the original graph. To illustrate why we need a reduced dimension size for the embedding, let's contrast this with a naive approach. So a naive numerical representation of a node can simply just be a one-hot encoding that is the same size as the number of nodes in the graph. This naive representation doesn't scale because for a graph with, let's say, 1 million nodes, for example, each node would have a representation size of 1 million, which leads to a memory requirement of 1 million squared just for representing the graph. By contrast, a node embedding with a small fixed length vectors allows our memory requirements for the representation to be linear in the number of nodes, with just a small scaling factor attached. The node embeddings also capture essential task-specific information that allows the downstream model to better perform node classification. Let's see an example of what this looks like. The graph here is the Zachary's Karate Club graph that shows the relations between 34 members of a karate club that was then split into 2 factions. A popular node classification task is to predict which of the 2 factions each nodes end up in after the split. The graph shown is color-coded according to the various communities that exist within the network. A good node embedding would preserve the community structure in the embedding space. Now, we can see a visualized learned node embeddings for the Zachary's Karate Club graph in 2 dimensions. We can see that community structure in the original graph is encoded in the node similarities in the embedding space. Specifically, using cosine distance as a measure of node similarity in the embedding space, we can see that nodes in the embedding space that are close to each other tend to be connected in the original graph and be part of the same community. It is easy to see how the task of training a node classification model in this embedding space reduces to finding a separating hyperplane in the embedding space. Now that we have an understanding of what node embeddings are meant to accomplish and how node embeddings make machine learning on graphs easier, let's see how these node embeddings themselves are generated. One class of techniques for generating node embeddings are the traditional graph learning techniques. The traditional graph learning techniques relied on either generating embeddings by manual feature engineering or using unsupervised dimensionality reduction approaches. And there are drawbacks to both of these approaches. First, generating embeddings by manual feature engineering often involves a combination of subject matter expertise on the domain that the graph is representing, as well as manual computation of network properties. On the other hand, unsupervised dimensionality reduction approaches don't involve as much manual fine-tuning, but are limited in other areas. There are 2 main techniques in the unsupervised dimensionality approach. The first kind of technique involves performing matrix factorization or tensor decomposition on the graph similarity matrix representation of the graph. Examples of these kinds of representations include the graph adjacency matrix or the graph Laplacian matrix. The graph adjacency matrix is essentially a matrix that consists of ones where every node in the graph is connected to any other node and zeros along the diagonal. This approach mostly employs linear or bilinear models for the matrix decomposition, and as a result, they are not able to represent other interactions in the graph unless those interactions are captured already in the similarity matrix. The other unsupervised dimensionality approach are the random walk-based techniques, which are similar to one-to-vec type approaches in natural language processing. Since the random walk-based techniques use random walks to generate a sequence of node visitations and then train embeddings to reconstruct those sequences, these techniques can actually capture higher order interactions. However, this technique does not allow for a natural way to combine rich attributes of nodes or edges when they are present with the network structure or topology. In addition, these techniques do not allow for end-to-end learning of the node embeddings and the downstream classification model simultaneously. In order to address many of the limitations of the traditional graph learning techniques, we will use neural networks for representation learning, graph neural networks specifically. So what are graph neural networks? Well, graph neural networks are a family of neural nets that can learn node embeddings in addition to edge embeddings and graph embeddings. These graph neural networks, or GNNs, work by transforming some initial features or representation of the nodes of the graph into a final representation of that node that is informed by the graph topology and the node neighborhoods. Unlike traditional graph learning techniques, GNNs can learn these representations inductively. This means that GNNs can learn embeddings that are not specific to the particular graph that the GNN was trained on. Essentially, the GNN can compute embeddings using the learned GNN parameters plus the graph structure, the initial node features, and any edge features. A GNN typically consists of more than one graph neural network layer. At each layer, each node's representation is informed by the representation of the node's neighbors from the previous layer. Between each layer is a nonlinearity, typically ReLU or rectified linear units. Subsequent layers then recursively use the representation of nodes from the previous layers so that the GNN is able to nonlinearly integrate topologically distant information, unlike the traditional graph learning techniques. While GNNs can be trained in an unsupervised manner to generate good embeddings for the nodes of the graphs, GNNs can also be jointly trained with a downstream classification model in an end-to-end fashion for additional supervision. DGL is a toolkit that makes it easy to do deep learning on graphs and train graph neural network models. DGL is built on top of popular deep learning frameworks like PyTorch or MXNet as the backend. In addition to model definition, automatic differentiation, and accelerator offloading capabilities of the backend deep learning framework, DGL also has pre-built functionality for graph-specific deep learning. For example, there is a graph API that allows the creation and manipulation of both homogeneous and heterogeneous graphs. The NN modules have pre-implemented graph neural networks for the popular graph neural networks like GCN, GAT, RGCN, GraphSage, and many more. DGL also allows you to build custom graph neural networks using the message passing interface, and it has many common graph algorithms like BFS, DFS implemented. The solution implements and adapts a few of the DGL GNN models for fraud detection. So let's go into the specifics of the solution. At a high level, the fraud detection solution trains a graph neural network that accepts an interaction graph as well as some initial features. In order to classify nodes as potentially fraudulent or not, this approach ensures that we detect signals that are present in the features as well as in the connectivity structure of the graph. The graph and features that are passed into a GNN layer uses message passing to recursively learn representations for the various entities in the graph by refining the original features and other initial representations until the final representations of the nodes in the graph are informed by both the initial features and the local neighborhood structure for each node. The default GNN model used in the solution is RGCN. Since the input interaction graph is a heterogeneous network that consists of many kinds of different nodes and many kinds of interactions between those nodes. After the final GNN layer, the refined representations are extracted and then passed into a feed-forward multi-layer perceptron that acts as a classifier and predicts the probability likelihoods for whether each node embedding corresponds to a fraud or not. The predictions from the classifier can then be supervised using the ground truth labels for the nodes in the training set. In order to do this, we set up a loss function like softmax cross entropy, which penalizes misclassifications at the final classification layer. And then we can train the full system end to end. We use backpropagation to compute the gradient of the loss function with respect to the parameters, not only in the classifier layer, but also in the GNN layers. So using DGL on Amazon SageMaker makes the solution to be scalable and allows for efficient model training for graphs that can have thousands of nodes as well as graphs that has millions of nodes and maybe even billions of edges. Compared to other graph learning frameworks, DGL is also built to have fast performance even as the scale of the graph changes by various orders of magnitude. Finally, running DGL on Amazon SageMaker allows for a fully managed experience where you don't have to manage your GPU servers yourself and you only pay for what you use during data processing and model training. The graph neural network models in the solution are trained using Amazon SageMaker infrastructure, and the solution itself is contained within an AWS architecture that can automate the detection of malicious users as soon as sufficient data is collected on user behavior. As soon as sufficient data is captured, putting the data in an S3 bucket under a particular prefix will trigger a Lambda function that will create a SageMaker processing job to process that data and generate features. Once the Amazon SageMaker processing job is complete, the processing data will automatically be stored in the S3 bucket under a different prefix. The data in this new prefix will trigger a second Lambda job, which will create an Amazon SageMaker training job to build the graph, train the graph neural network model, and make predictions for nodes that are in the test set. The results of the model's training job are also then fed back into the same S3 bucket under a different prefix. Finally, there is the option of having a third Lambda function that takes the model predictions and performs some post-processing. For example, we can send a notification to Amazon SNS or update a table in Amazon DynamoDB. To run the solution as a manually driven demonstration, there is also a SageMaker notebook instance which contains a Jupyter notebook that abstracts the full end-to-end functionality of the solution and allows you to invoke the components of the solution by running the cells in the notebook. The notebook also uses similar SageMaker processing jobs and SageMaker training jobs to do the data processing and model training respectively. In this part of the video, I will show you a demo of how to launch and run the fraud detection with graph neural network solution. So here we are on the GitHub repo page for the graph fraud detection solution page. And if we scroll down on the README, we can find this button I talked about earlier that allows you to launch the stack. So if we click launch stack here, this opens the CloudFormation launch wizard, and it has already pre-filled some of the parameters that we need to launch the stack. All we need to do is add a unique name for our S3 bucket that the data and the models that are launched in the solution are going to be stored in. So here I can call this something like graph fraud detection demo. And this will ensure that the S3 bucket that's created as part of this launch process is going to be called this. It is important to use a unique name because S3 bucket names are meant to be globally unique. So a good tip for this is to maybe include your AWS account ID or some randomly generated hash code in the bucket name. So here we click that we acknowledge that CloudFormation is going to create IAM resources for this launch, and then we can click create stack. So when you click create stack, this is going to launch the CloudFormation stack, and you should see a screen like this, right? So this is a stack that I already pre-launched before I started recording this demo. And when you launch your stack, this is what the end product should look like. So at the end, we can see that like all the resources in the stack have been created, and in order to actually verify, we can click on the resources tab, and this shows us all of the different resources that were created by the stack. So we have 10 different resources corresponding to the Lambda functions, as well as the notebook instance and all the permissions rows that are required for the resources to be able to run and access data from each other. Finally, you can click on the output tab here, which has convenient links to the notebook instance that we're going to use for the end-to-end demo, as well as all of the source code that's available on GitHub where it ends up on your SageMaker notebook instance. So if you click notebook instance, this should navigate directly to the fraud detection main notebook. And this notebook essentially contains a step-by-step instruction of how to run the entire process that we talked about earlier in the presentation part of this demo. So first, we're going to import SageMaker, and then we're going to assign the role that we're going to give to the SageMaker sessions to run the processing jobs and the training jobs. So the way we do that is essentially by just running import SageMaker, and then from SageMaker import get execution role. So I have already pre-run this particular notebook, but if you wanted to run this in one go on while you're running the demo, you can essentially click on cell here and then click on run all. And this will run the entire notebook end to end, and you'll be able to sort of follow this demonstration. So the first stage is sort of data preprocessing and feature engineering. The data that we're using is this IEEE CIS fraud detection dataset, which is a kind of typical example of financial transactions dataset. The dataset consists of two relational tables. The first table is the transaction table, and this transaction table essentially records transactions between two particular customers of online financial service. Right? So when a particular customer initiates a transaction, that is recorded in this transaction table, in addition to how much that transaction was, who the recipient was, and other sort of metadata about the credit card or financial instrument used in the particular transaction. The identity table actually contains information about the user that's initiating transactions, and it contains information, for example, of like what kind of device they're using, as well as other sort of like network identity information, like what cookie session, what IP address they're making their request for, and so on. So what we will do here is we will move the raw data that's stored in a S3 bucket into the S3 bucket that's created by the CloudFormation for this solution. So like everything can be in the same sort of S3 bucket. And so we point to the raw data location in this particular S3 path. But if you wanted to run this demo on your own data set, then you'll change this raw data location into a different S3 path where your own data is located in. So the bucket here is the bucket that we sort of created when we passed in the bucket parameter into the CloudFormation stack creation process. Now this bucket is sort of automatically pre-filled because when the CloudFormation runs, it knows what bucket we want to use for the solution. All right, and for all of the sort of training artifacts and data preprocessing artifacts for this DGL-based fraud detection solution, it will be stored in this DGL prefix. So here we're just copying the data from where it is in the raw data location to the S3 bucket in our account. And we also set the S3 locations where the output of the processing job will be stored, and also the output of the training job. Right. So this is in order to have this location set for down the line when we run data processing and model training. So here we're going to sort of be using SageMaker processing for the data pre-processing step. And SageMaker processing essentially requires you to create a pre-processing container that contains the environment that you need your data pre-processing to run in. Right, so because data pre-processing and feature engineering is an important part of the machine learning lifecycle, Amazon SageMaker has processing jobs that allows you to do this easily on managed infrastructure. So the solution comes with pre-built container definition in this in the data pre-processing folder. We have a container subfolder that defines what the data pre-processing environment should look like. Because this is a sort of minimal data pre-processing, we only use pandas. Pandas is essentially the only requirement because all of our data pre-processing can be done with the pandas library. Once we sort of create the container, we can then use this script called build and push to push the container to an ACR repository. And so this ACR repository is going to store the container image. This is the repository URI that will be used by the SageMaker processing job when we want to run the processing job. So here we're seeing the output of building the container where we're installing pandas and some other additional pandas dependencies, and then we're packaging the dependencies into a container image, and then we're pushing the image to the particular ECR URI. So once we have the container environment for the pre-processing job done, now we can run the actual pre-processing step using Amazon SageMaker processing. So here we are using the script processor, which is essentially a class that SageMaker allows you to pass in a data pre-processing script along with container image for the environment, and it will run that particular script in the container image. So the script is defined at data preprocessing graph data preprocessor.py, and it performs the data processing that we're doing in this particular project. So the data processing steps include performing numerical encoding for the categorical variables, and then we're also applying a logarithmic transformation for the transaction amount. So this allows for essentially the features to encode the relative amount as opposed to the actual amount, right? So we encode the relative magnitude of the transaction amount as opposed to encoding actually how much was transacted. The data pre-processing script also constructs the edges that are going to be used during graph construction and model training, right? So it will parse the two tables that we have and extract sort of edges from the relational tables and then save that into a CSV file that contains a list of all of the different edges. Now, because we're constructing a heterogeneous graph, we will have a single CSV file per relation type. So here we sort of define the script processor with the particular command that we want to run, which is Python 3. We pass in the ECR repository URI, which corresponds to the container image URI that we sort of created in the previous cell. And then we pass in the sort of execution rule that we sort of created at the beginning. And we say we want this script processor to use the M4X large instance type. So once the script processor is defined, we can run it with a particular data preprocessing code. And so the data preprocessing code is defined in the graph data preprocessor.py file, right? And the code essentially expects the input raw data to be in this particular directory on the processing instance, and it's going to save the result of the processing to this particular output directory. Now, our data preprocessing code essentially accepts arguments, and these arguments are sort of specific to the data that we're passing in, so that the script processing code can do the feature engineering properly, right? So for this particular graph fraud detection use case, we essentially have three kinds of columns that we expect in our data set. The first kind of column are the identity columns, and these identity columns sort of correspond to attributes that have something to do with the identity of a particular user performing the transaction. So here we have some information about what card type, as well as what the user's maybe email domain is or the address domain. Besides the identity columns, we also have the categorical columns. So categorical columns are columns that are categorical but not identity. And so for these categorical columns, we need to perform sort of numerical one-hot encoding to convert them to numerical columns. For all of the data set that's passed in, any column that's not an identity column or a categorical column is assumed to be a numerical column. And those particular columns will be left as they are and just used as part of the features. So here you can see logs that are generated by the processing job as data preprocessing happens, right? So we first do a train test split where we take about 20% of the transactions and use that for testing our model. And then we can see that our fraud detection problem is pretty imbalanced because we only have about 3.5% of our transactions being labeled as fraud. We also sort of see the columns that correspond to the categorical columns that we passed in, and we see what happens when after the feature transformation for these categorical columns. So we have a bunch of all of these other columns are numerical columns, but at the end of this, we can see that our categorical columns have been one-hot encoded, right? So for M1, we had two categories, true and false, and they've been one-hot encoded into M1F and M1Z. The second part of the data preprocessing code sort of corresponds to preprocessing the identity columns. And these identity columns are going to be used to construct the different relations in the graphs, right? So here we can see these are the identity columns that are going to be used to construct the relation types. So we have information about the card, but also information, network information about the user, corresponding to maybe the user's IP address, the user's MAC address, the user's device ID, and so on and so forth. And so we write each of these identity column and we make a sort of set of edges between a particular transaction node and a particular identity node and write this into a CSV file that corresponds to a list of edges for a particular relation type. So one example of a relation type would be this relation between the transaction and card 1, and then that becomes a particular edge list. And in total, we have about 40 of these relation types. Once the data processing job is complete, we can actually look at the results of the data preprocessing where it's stored in S3. So we can see the various S3 paths for the features that have been transformed, as well as all of the different relations. that we construct from the identity columns, as well as the labels or the tags that correspond to whether a particular transaction is fraudulent or not, and the nodes that are going to serve as our test data set. Now we're ready for training the graph neural network. So as I mentioned in the earlier part of the presentation, our graph neural network will be based on the RGCN GNN. So RGCN is Relational Graph Convolutional Network, and RGCN is essentially a type of graph neural network that is good for representation learning on heterogeneous graph. And because we have different kinds of edge types or relation types, RGCN is a very good choice for this. The way first we're going to define the hyperparameters that are going to be used in the training job. So we have a small subset of the hyperparameters that need to be set. Well, the node features are going to be contained in the features.csv file from our data preprocessing step. The edges are sort of the files that correspond to files beginning with relation star. Right? So this is our sort of regex expression that will evaluate to all of these different relation files that contain our edge list. The labels are in the tags.csv file, and then we're saying we want to use the RGCN model, and we want to run this on using just one GPU. And because DGL allows you to do sort of mini batch training for large graphs, we're going to pass in our batch size as well as the embedding size and the number of layers of RGCN we want to do. So here we're using just 2 layers in order to be able to run this quickly for the demo. And we'll run this for only 10 epochs and use the Adam optimizer. So these are just a subset of the hyperparameters that you can set. If you look at the estimator _fn's Python script, you will see the defaults of all of the other hyperparameters that are set for the GNN model. So here we're just listing all of the files that are going to be used as edges to construct the graph. Once we set the hyperparameters, now we can define the training estimator. So because we're using the MXNet backend for DGL, we're going to use the SageMaker MXNet estimator. Now the SageMaker MXNet estimator already has DGL installed on the in the estimator container as one of the dependencies. So the way to use this is to sort of create a SageMaker MXNet estimator and then pass in the training entry point script. And so this training entry point script you can sort of see in the GitHub, and this is essentially just defining the functions that are going to be needed for performing training on the model. And then we pass in the source directory, which contains this entry point script as well as other sort of utility functions and different files that make up the whole training package. And for this particular estimator, we're going to be using a P32X large, which is a GPU enabled machine. And we want to use the 1.6, which is the most recent version of MXNet available on SageMaker. We pass in our hyperparameters here, and then we also pass in where we want the estimator to store the training outputs and where we want the estimators to store the code that is used on the estimator. And so finally, once we have the estimator, we can call estimator.fit and then pass in the training data. And passing in the training data, if you recall, the training data is set above here, and it refers to essentially the S3 location where the process data is stored. So we call estimator.fit, and this launches a sort of SageMaker training job, and it gets all of the dependencies for the training job by downloading the SageMaker MXNet estimator, and then also contains DGL pre-installed, and then sort of sets some environment variables that are necessary for the job before the training job starts. And so we can see that like we're using all of the we're using all of the edge lists that we created from the pre-processing step to construct the graph, right? So we read in all of the edges from these edge lists, and then we also read in the features, and then we construct a heterogeneous graph that has the following metagraph structure, right? So the metagraph structure corresponds to all of the different canonical edge pairs in the graph, right? And so we can see that like we have a relation between our target node, which is the transaction node, and ID 21. And this, we have this repeated for all of the different sort of relation types. We also see some sort of statistics of the graph when the graph is constructed. We have roughly 700,000 nodes as well as 10 million edges. And we can see that like the features sort of correspond to the number of transactions in the graph. So here we the estimator is initializing the model, and it initializes a heterogeneous RGCN model like we said we were going to use earlier, which has 2 RGCN layers as well as a final multi-layer perceptron or a dense layer that does the final classification. And here we can see all of the parameters that are involved in the hetero RGCN network. Once the model is defined, then the training instance can start training the model. And we can see that like as the model trains, the loss is actually going down. And we're also reporting like how long it's taken to sort of train the model. Once we've done the sort of once we've trained the model for the number of epochs that we passed in as a hyperparameter, then the training script sort of prints some metrics that show us how the model is doing so far, right? So here we can see like we have an accuracy of 0.96%, which is pretty good, but our precision and recall are, because the model hasn't trained for long yet, our precision and recall are still not up to the same standards. But we can see that the area under the ROC curve is also already pretty good. So training this for longer will actually lead to better results, in addition to sort of trying various hyperparameters and using a larger number of graph neural network layers or using a deeper GNN. Right? And once the training job is complete, everything is all saved and stored in S3. So this just shows an example of how you would run data preprocessing and model training for the graph neural network. And once you train your model and you're sort of happy with the results, the sort of options for what to do next include like saving the model predictions immediately to, say, for example, a DynamoDB table, or you can sort of deploy the model as a SageMaker endpoint and get just-in-time predictions. So now I'm going to switch back to the presentation to sort of wrap up this video. Now let's get into how you can get started on the solution. All the code for the solution is available on GitHub at the link shown here. The project on GitHub also contains CloudFormation templates that make it easy to deploy the project into your AWS account. Simply click Launch Stack on the GitHub repo landing page, and then a CloudFormation wizard will be launched that allows you to deploy the resources in this project to your AWS account. So finally, here are a list of resources to help you with any additional implementation guidance that you might need to take the solution and apply to your use case. The solution source code and deployment guide is available on GitHub, and that's the link. I've also linked the DGL GitHub repo, which contains other examples of training graph neural networks to solve other problems. And I've linked a page on the SageMaker documentation guide that shows how to use Deep Graph library on Amazon SageMaker, and points to a number of different examples of using graph learning on Amazon SageMaker. So thank you for listening, and happy building.